in the Intro Programming webcast session today. And today we'll be focusing on object-oriented programming. Some people may be at stage 3 already who are taking Kunal's course and who are looking at how you would do object-oriented design. And some people may have not gotten there. So if you feel like the concepts that we're talking and the code that we're sharing with you, if it doesn't make sense, feel free to pause the video. Make sure you work through stage 3 first before you come on and look at this webcast session.
Come back through. It'll always be here recorded on the forums and on the Google Plus page, so you can always come back and watch it later.
Yeah, so I highly recommend it because we will not go over the basics of object-oriented programming. We assume that you know the basics already through stage 3 because the stage 3 videos will actually tell you how you would do basic object-oriented programming. So this is for people who want to learn how to apply this sort of stuff. Like if you need more practice, if you want to see another application, something a little bit more real world, I think would be good. So this is a perfect webcast for the students who are at that stage already.
Yeah, actually I have a question right before we start.
Yeah.
It's a good thing to start off with. What is the main difference between what we've been learning, like procedural programming, and then what we're learning now, which is object-oriented programming?
Yeah, so procedural programming is step-by-step instructions. So basically, you start from top to bottom, and that's in a nutshell. You start everything from top to bottom, and you never go back to the code. Object-oriented programming, you start from top to bottom, but you also go back. That's in a nutshell. You go back. You actually tell the program, okay, this is what I programmed before. I want you to keep going back and keep executing this code that I want you to do as an object. And furthermore, the main difference between procedural and object is that procedures, there's no such thing as objects. And basically, an object is defined as it's a state. It's an entity that contains a state and contains actions to interact with the world, like an outside world or an internal world, like a programming system. Because basically, if I can give you an example, this is an object. This is a dry eraser marker. So the state and the attributes is black, cylindrical.
It's erasable.
It's erasable. Yeah. And an action is that I can actually use this to write. So I can actually think about programming. If I were to simulate this in my programming, in the programming world, like in the computer, I would tell the computer, this is an object. And I'm going to tell it, okay, every object has the ability to hold a shape, called a cylindrical shape.
Yeah.
Has an attribute to be black. And it has the ability, I'm going to write a function called write.
Yeah. So
then each object has the ability to write by itself and on its own. So we'll show you right now how of the application that we'll be building today, and how it'll be very, very hard and very error prone if you were to use procedural programming versus object-oriented programming.
Okay.
Do you have anything else to add, Jonah?
Not for right now, but a little later.
Okay, great. So let's click done here.
All right, let's dive in.
Let's dive in. So I'm just going to show you in the next 30 minutes or so, 40 minutes of what we'll be building. So I'll just show you right now. So basically, you see me screen sharing? Yeah. Okay. So basically, if I go here we go.
Very cool.
Very cool. So this is actually an application that you can build in Python. We're going to give you all the starter code and also this final code as well. So you can all go back and code along and try to understand the parts and processes that's involved in object-oriented programming. In this case, you can see it's a simple program. It's a graphical program.
Yeah.
So this actually, for a lot of people, this is probably your first time seeing colors and not the terminal, not just a text-based interface, but this is now we're diving a little bit into the world of graphical user interface, or GUI programming. And yeah, there are a ton of libraries that Python has, so you just have the ability to use these libraries to be able to build these sort of graphical interfaces. Great. So that is what we want to build. And our starter code. This is our starter code. I'm going to just run our starter code right now. It's just this, and that's it. So and yeah, there's no edge collision. We need to program that in, but you can see that it's a very basic program that actually goes in and animates a circle. I'll just say these are balls, just to make everyone understand that we're trying to animate some balls on the screen. So here are the things that we're gonna go and talk about and learn throughout this webcast. Number one, I'm gonna dive in and talk about the theory of animation and how to implement animation in a program. So it's pretty simple once we decompose animation and what animation really is. So hopefully after this webcast, you'll be able to understand, basically the magic behind animation in computer graphics and computer programs. So any animation that you see, this is actually the building blocks of anything else that you'll see in computer graphics, computer programming. Then Jonah,
yeah, we're gonna dive in a little bit deeper into the code and then see actually how these circle objects are created in Python, and then how it sort of derives from other classes that we've created, like shape, and sort of see the nitty-gritty about how class methods work, how instances work, and how method overriding works. I know that you've heard these terms before, but we can see it happen live right in front of us. It'll be cool. And then later on, we'll see how we can make this a full-featured program by making the circles hit the edge and then bounce back in a way that's believable, and in a way that looks kind of cool in the end. Yeah, that's all doable in a few lines of Python code, so it'll be fun to see how it comes together.
Awesome, great. So can we switch back to just our camera?
Yeah, definitely.
Awesome, great. So let's talk about animation, the theory of animation, right? So it's like, Jonah, have you, when you're growing up, have you ever used a flip book?
Yeah, those are fun.
Those are fun, right? Basically, you have a flip book, stacks of paper here, you draw something, and then the next page you draw the same object, like say a character, like say Mickey Mouse or something like that. Then, but Mickey Mouse slightly changes.
Dances or something.
Yeah, he dances. So, and on every paper and on every frame, the image slightly changes.
Right.
Not too much, but just enough to be able to say,
Make
okay,
you believe
that it's moving. So basically, animation in computer graphics and movies and film is just a series of still pictures. And
it's all a lie.
It's all a lie, really. Basically, it's an illusion. That our eyes, thing is, our eyes cannot, above a certain point, like I'll think 60 frames per second. Like if your eyes will not be able to see, like let's see, the stop motion cameras, or those high FPS cameras,
right.
Because if it's a high FPS camera, like at 2,000 frames per second, it can record it. You'll be able to see things like doing this. If I drop this, you'll be able to, at a high FPS camera, you'll be able to see this, because it's fast enough to see these frames, so it looks like this. So if our eyes cannot process that fast.
Oh, you mean if you mean like a high FPS camera, we're filming a film.
Yeah, filming this pen dropping.
Right.
Like it will look like this.
Right. Yeah.
But our eyes, it will just look like this. Yeah. Same thing. It's like we're just basically fooling our eyes because we can only display, displaying at 50 frames per second.
Right.
If it's like 50 frames per second, this is an image, this is an image, this is an image here. It means that it gives us the illusion that the picture that we see in the frame in the picture is actually moving.
Yeah. Movement.
And that is the whole big theory of animation right now. So let's take a step back and reflect on what it means. Animation is just really a series of pictures. Okay, we have this basic theory. How do we actually apply it in programming? We basically tell the program, okay, I want you to display this picture many times in rapid succession. So basically, what does that mean in computer programming? In rapid succession, I want to draw a picture, about the same time, but then I just change the picture a little bit.
Yeah.
That's maybe can I just call that function over and over again? let's say I have a function that draws something. Can't I just draw it?
Yeah.
Then wait a certain amount of time, very little time, and then draw it again.
Yeah.
Create a function, wait, execute it, then wait to then call this function again. Draw. So that's basically how we're actually going to implement animation. So let's go back to the code.
Yeah.
We'll show you how the animation will work out. And don't worry, we will give you all this starter code when we post our notes in the discussion forums. So basically, our animation is basically made up of, this whole application is made up of these things right here. And this is the constructor. So again, if you should have been able to, if you're going through stage 3 or you finished stage 3, you're familiar with constructor function. So whenever we create an application like this, an application frame app, I have a constructor function. So it will actually, upon object creation of this application, it's going to actually execute these steps. So I'm going to use, so this is, oh, by the way, the library that we're using is called Tinter, A-I-N-T-E-R. So basically, what this says is like, I want to inherit a frame object and then basically call the constructor for the frame object. I'll then put on line 18, self.grid, I will then put this whole application and make a show, because it's not enough that if I create the object, I need to make a show on the screen. Then after that, great, I'm going to create all my widgets. And my widgets is just things that I want to put onto my application screen. And in this function, this create widget will actually create my canvas object. And we're going to be using an object called the canvas object. And the canvas actually has functions that help us draw things. So without the canvas object, it will be harder for us to actually basically physically access the screen and then paint the pixels on the screen, because we will have to figure out how to do it ourselves. But this library gives us the ability to draw shapes, prepackaged, draw shapes, put pictures on it, put pixels on it pretty easily. And then I'm going to create my canvas objects. And in there, my canvas objects is actually my circles, my balls. And then I'm going to call this function called animate. Okay, I've created my initial state. I have certain circles and balls, and then I'm going to actually call the animate function to actually start animating things. So let's go down to the animate function, __ animate. And by the way, caveat, __ in Python means that it's a private variable. So I'm creating these private functions as well to tell, like, yeah, this is a private function. You should not access this method animate outside of the application object. You should never access that. So let's go down to animate.
Can you talk a little bit more about the difference between like private and public functions?
Sure. So private functions and variables are variables that you define in your object that's an internal state.
Where it stays.
Where it stays, you don't want other programmers to access it, because again, it's internal. It's similar to I'll say, let's imagine that an object is a person.
Okay.
I want to be able to access the breathing rate of a person.
Right.
I don't want to actually literally go in and take your lung. And
yeah,
it's crude, but it's kind of like that.
Right.
You
ask them, you're like,
yeah, can you?
You measure it.
You measure it. So basically, there's probably a function called ask breath rate, and then the person will know, okay, I'll put my mouth on the breathalyzer and I'll breathe into this machine, versus you just literally taking my lungs out and examining it.
Right.
Because if that happens, there's a whole potential world of problems that you can run into.
Yeah.
If you were to mess with a person's lungs directly, that's bad.
Yeah.
Even accidentally, even if you have the best intentions, these private variables are private for a reason.
Don't be messing with other people's organs.
Yeah, that's I will say that it's a very crude analogy, but I think the analogy works.
No, I understand. Yeah.
It's so that's the reason why we have this notion of public variables, and these are public facing functions that you should use.
Yeah. Okay.
Don't mess with the internal implications that I'm setting up in my object. They're meant to be, they're there and they're not meant to be accessed.
And then how do you separate them? How do you know something's a private variable as opposed to?
So as I've mentioned before, in Python there's this underscore.
Right. Gotcha.
So you'll often see a lot of, if you're diving into a function or an object, you'll often see underscore, or in the functions or objects definition.
Yeah.
That means that these are private. You should not be playing around with them.
Yeah.
You can always investigate and see what they're there. Whether if you're trying to understand how they're implementing their object, but using it, I don't stay away from those.
Okay.
Good question though.
Yeah.
Okay, so animate. Here's the whole animate function. This is actually the whole secret to animation. This is the magic. It's what? Less than 10 lines of code, actually. All right, so here you go. And you think about like, wow, this is it. Well, yeah, this is it. Yeah, it's basically here's 3 stages of animation. One is I update all my objects' positions, and in this case, I update their x and y coordinates because we're using a coordinate system. This is how we place objects on the canvas. We use a coordinate system. So x-axis, y-axis. If you're going back to your algebra days, where you're trying to graph an object. So yeah, there you go. So you should have paid more attention in math class. This actually applies directly if you understand the Cartesian coordinate system. So I have a function that says update everything. Go through all of my objects and update their position. So basically, if I go down here, update all is with my starter code. I have only one circle. My circle left is my coordinate. It's basically my my x-axis. And then I'm adding 250 over FPS to what number the circle left is already. So in theory, if I have circle left is equals to 0, the next frame or the next second, I move it 250 pixels for every second. Then the next second, it's going to be at coordinate 250. So that's how you update things. And let's go back and do a redraw. Now, here's the thing. That's why we call this a canvas. We need to, if we're painting on a regular canvas, it means that if you put paint on your canvas, that's pretty much it.
Yeah.
You can't really, it's hard to erase the pixels or erase the paint on the canvas. And that's why we tell people, especially in programming, we use that analogy. That's why we use the term called canvas. If you paint pixels on the canvas, it will not go away unless you tell it to physically erase it. So therefore, if you were to paint and repaint on top of the canvas, it's not going to look like the circle is animating. So let's actually comment this out. I'm not going to clear everything now, so I'm actually going to run this program. Ooh. Self redraw. Oh, I'm not even redrawing. Here we go. Here we go. I'm going to do this. So I'm not deleting all the stuff on my canvas. I'm just constantly drawing things over and over again.
Okay. So it should make a line.
It should make a line. See?
Oh, there it is.
There it is. See? And that's not what we want. Sometimes we want that. If we were to want to draw a line, draw a series of pixels, then we don't refresh the canvas. We don't erase what's on the canvas at every frame. So let's go back here. There we go. So basically, redraw all basically tells them like I'm going to delete all my existing pixels, and then I'm going to actually call canvas the kind of canvas object here. And there's a function called create oval, and then you actually feed it the coordinates here. And the fill color is the circle color, and then the width is 0, the border width. So then this will actually draw the circle.
Okay.
Now let's go back. This is still how I set up things like the class application. That's an object, but that's like boilerplate stuff.
Right.
But if we were to not use object-oriented programming for our objects itself, Jonah, I want to ask you, okay, give me 30 objects.
Yeah, that would be tough.
Like, why would it be tough? Here's the code to create this one object here.
Yeah, I mean, we can do that. We can just copy and paste, and I'll do it 30 times.
Yeah,
and that'll be fine. I can do that.
How about if I want to say, okay, I want some of the circles to be green?
Oh, how many circles do you want to be green?
Well, it's 10 green circles, and I want maybe the velocities to be different. I want them to start at different locations.
Sounds like too much work.
Right.
Sounds like I want to do something that could automate that work for me.
Right. So this is in the procedural world. We don't have any sets of objects.
Yeah.
Like internal representation of an object, right?
Yeah.
So, and here's where the rubber meets the road. I know there was a question asked, like, what's the whole point of what's the advantages of object-oriented programming? This is right here. If I tell you I want you to create 1,000 objects, let's say I want you to create a particle system in some sort of like a game, like a particle system. 1,000 objects is nothing, right?
Yeah. You need 10,000.
You need 10,000 plus lines of code to actually create all those objects, those little circles, and then change them, and then figure out, okay, well, I have 10,000 lines of code. I only want to find maybe 500 of those. I want to actually change the particle movement for only 500 of those circles. You could clearly see that you're going to be just lost hunting down, going through 10,000 lines of code.
Yeah, it takes way too much time. It's not an efficient use of your time. It's going to slow down your computer if you have all these things and you're trying to change things on the fly with 500 objects at a time, or not objects, 500 lines of code at a time. You're trying to change them on the fly. It's going to slow down your computer, and it's not going to be a good experience for the user.
Yeah,
and that's what counts in the end.
Yeah, and development time will increase.
Development time increases. If you ever want to change anything, you need to debug.
Yeah,
that's going to increase.
It's going to increase. If you're working with other developers, they're going to hate you.
Yeah, that's true.
That's true, right? Like other developers will say, "All right, great, you created this. Give me your code to create 10,000 objects. I need to work on the user interface."
Yeah.
And they're like, "Holy cow! Yeah. You just gave me 10,000 lines of code. This is not going to work."
People will talk behind your back and be like, "There's no abstraction. Your object-oriented programming is."
Exactly, and then that's not good. So now Jonah and I are going to exactly how we actually convert this implementation to more an object-oriented design.
Yeah, absolutely. I mean, you guys have run into this sort of thing before in CSS. You don't want to style things on the fly. It's really similar with object-oriented programming in Python. So rather than creating those 4 lines of code that you see here that Mark highlighted, we can take this idea and create an object for it. So like we were talking about earlier, we'll make something like this expo marker, except it's going to be on the computer and it's a circle. So what do we think about? What's like the most general idea we think about when we think of a circle? So a circle is a kind of shape, right? So when we're talking about programming, we want to think general and then more specific. So we'll start with making a shape, because let's say later on we want to make squares.
Good point. Yeah.
Yeah. Or we want to make corgis.
There you go, dogs, right?
Yeah.
The shapes,
it's a kind of shape.
It's a kind of shape, a dog shape, but exactly. Still, you can still animate, get a picture of a corgi, or actually, draw out the actual specific shape of a corgi.
Yeah.
There's options for you to draw that out. So.
Yeah, anything's possible, but it's only possible if you allow it to happen later on. So you want to be forward-thinking when you're programming. So we start with creating a shape class.
So let me go here.
Yeah. So
class shape here.
Class shape. So we started defining this in our final version of this code. And what are some things that define a shape? So we can think about where it is on the canvas. So I have balls that move around the canvas, and they'll be in different spots. So that's their position. They're going to have a velocity, which is going to be their direction as well as the speed. They're going to have a certain width and height, so we all want to code all these things into them. So this is how we do it. If you look closely in the code here, we initialize it. Whenever we create a shape, we want to initialize it, and we're going to pass in all these variables that we just talked about. We're going to pass in the velocity, the width, the height, the color, the canvas width, the canvas height, and then this X and Y values. So we want to create these randomly because we're just going to put them on the page, make them do whatever they do, and then have them bounce around, and then it'll look fun in the end. So the way this works is we assign the X value of this shape to a random integer between 0 and the canvas width minus the width of the circle. So this makes sure that your circle is within your canvas, because you want to make sure the circle is where it is. So make sure that you're not beyond the edge. Same thing with the Y value. You want to make sure it's on the page itself. Then we assign the width of the circle to all the values that we created, the height, the color, and then also we pass in the velocity as a list. Since it's going to be 2 values, we want to put in the speed as well as the direction.
So actually, these are X and Y. So the list valid velocity is X. It's just X and Y. It's just an X and Y.
Okay.
It tells you the direction and the magnitude as well.
Okay, so the X and Y values are going to give you the magnitude of the direction.
And the direction at the same time.
Right.
So, and also I just want to point out why would we assign lists velocity instead of just the velocity equals velocity here. And the reason why I said like with lists, like other mutable objects, they act like pointers.
Right.
So if you pass in a pointer, you're basically passing in a reference to that same.
Right.
Look, this is getting a little technical. That same location in memory, and if you somehow change that, things start happening. So whenever you want to pass in a list or a tuple or anything that is mutable, make sure, and if you plan to change that, and make sure that you plan to only like really make sure that that state is preserved, pass in a copy of it. And a trick that a lot of Python programmers will do is like they'll use the list function to pass in the list, and that list function will create an entire copy dedicated just for that one object. Okay,
that's great, Mark. Actually, I didn't know about that.
Yeah, so that's why I added in the comments like we need to pass in this or else, because if you have if you're doing something in all the velocities somehow they're all the same, it means that like all of our objects are sharing or pointing to the same velocity.
Okay.
Whenever we're making a change for one object, it affects the entire system.
Right.
So we always need to make sure that we're passing in the velocities that will only be that one object.
That's characteristic to it.
Yeah, that's characteristic to that.
Okay.
So this is a big caveat here.
That's a great trick.
Yeah.
Or probably a really necessary trick at this point. Cool. Great. So if we look further down on this code, we see some methods that we define for this class shape. So when we use this shape, we want to have some functions that we can pull out of it. So we can call these getters and setters. So when we want to, like Mark was saying, we want to ask the shape where it is. We don't want to just go in and pull out its shape. We want to have this function called getVelocity, which will return that list velocity, which we defined earlier.
It's a copy as well. It's not the direct reference.
Yeah.
And that's actually very dangerous. You actually do it that way because it's very error prone.
Right. Yeah. So you want to pull out a copy of it so that you can use that and change it or pass something back in that's different without actually messing up the class itself. We also have a function here we can set the velocity. So this is going to be really valuable when we want to set the initial velocity of the circle, but then also later on if we want to change it. Then we have getting the position of the circle, and then we also have a function for setting the position of the circle. Do you have anything else you want to say about those functions, Mark?
We can move on.
All right, great. All right, so we have these animation methods within the shape itself. So we had defined earlier the general idea of animation, but it's going to be a little bit different for these circles itself. We want to have the shape's position be updating as we move through the code. So the way we do this is we take that self.x, which is its expedition, and then we add to it the velocity divided by the frames per second. So this gets a little bit technical here. Don't want to spend too much time on it, but it is going to be how we update the function as we go through, or how we update the shape as we animate it. You want to talk a little bit more about the how this animates the shape more further than what we had before?
Further than what we had before. Basically, in a nutshell, how we think about it, so like for every update call, because we're calling this update function every few milliseconds at a time. To be exact, in this program, it's 16 milliseconds per frame or per update. So every 16 milliseconds, I'm going to update the X position with a number. And this number is inspired by this velocity. And this velocity tells us, because it tells us a magnitude and direction.
Okay.
Tells me where I want to go and tells me how fast I want to go there.
Yeah,
so basically, we'll have more detailed notes that tells you why are we like dividing by FPS, but basically it's a good way for us to like say give it like 100, like a velocity of 100.
Yeah.
100 means 100 pixels per second.
Gotcha.
I want you to move at 100 pixels per second. In this case, if I divide this by FPS, since we're working in the realm of milliseconds, we need to convert that into the number of pixels per frame.
Gotcha. Okay, so basically each time the frame updates, it'll be that much further if it's faster. So if it's slow, there'll be less pixels per frame, and if it's fast, it'll be more pixels per frame. Okay.
Just if you're confused on that, I recommend just to work it out on pen and paper. When I was developing this application, there was I had to take a lot of notes myself and have to draw my vectors. I had to visually see how my animate things myself. So
that's what makes it kind of fun with this sort of programming. You have to like sort of think a little bit differently than you would otherwise. Cool. So let's dive into
the circle actually.
So now that we've defined a general shape, we can get a little bit more specific and talk about the actual circles that we're going to put on the page. So this is the fun part. So we are going to inherit the class shape. So the way we do that is we have circle, and then within parentheses we have shape. So this means that all the methods, all the variables that we used in shape get passed down to circle.
And this is actually very efficient.
Yeah.
Right? Because if I want to change something in the shape, I don't need to change 10,000 things.
Yep.
So this actually really helps you with maintaining your code base. So it's instead of this was like maybe 30 lines of code, we reduced possibly 10,000 lines of code to 30 lines of code.
Yeah.
So it's
huge.
This is a very powerful way of programming.
Yeah. So what we can do with this is we actually define a separate initial constructor method that's init here. So it's going to be a little bit different than the shape object. We're going to be passing in the velocity, the width, the height, the color, canvas width, canvas height, X and Y, all that's the same. But we're going to change a couple different variables in here. So we have the radius and the center. So why does that matter? If you think about a circle, what are the two things that define it?
Radius and center, yeah. That's actually really important, especially when you do some math, right?
Yeah, exactly. So whenever you're defining a circle in a plane, you just want to know where its center is and how big its radius is. And that's good. Since you know its radius, you can know what it's going to look like in the end. So the radius is going to be the width of the whole circle divided in half, because twice the radius is the diameter, exactly, which is the same as the width. And then its center is going to be the x value plus the radius, and then the y value plus the radius. So that's the center right here.
Some people will make it confused about that.
Oh wait, yeah. Let me should we draw it out here?
Draw it out here. So
we got some legal pad right here.
Some legal pad here. So
let's do that from the top.
So yeah, from the top. So how things we define a shape is an X and it's the top left corner, right?
Yeah.
It's the X and Y is when we define a shape in our canvas system, it's actually the top left corner. So here, there you go.
Yep.
We're going low tech here, everyone. So this is the top left corner. This is your X and Y. This is our general shape. This top X bar. So the information we have is X and Y, but we want to know the center here. So how do we get to the center from this corner?
Exactly. So we only know where the center is and then where the radius is. So I've drawn a line out here, which is the center and then the radius up to the top. And that's going to help us define our circle. Cool. So we got that right here. So the way we can work through this is we have the...
Okay, go ahead. We're still
on the
camera.
Camera here. So we can find the center by, if we know where the X value is, and we add the radius, that's going to give us, sorry, that's the Y value. If we have the center here and then the radius, that's going to help us to identify the center based on that information that we pass in. Same thing with the Y value. Right now, the Y value is 0, so we just add the radius and that gives us the Y value from the top. Is that?
Yeah, so basically, you add, here's your Y, you add in your radius here.
Yeah.
And then you add in your radius here. And then, so R going here, and then R going here. This is your center, R, because if X and Y is 0. So basically that's how you, in general, find a center for any circle, giving an XY position in the top left corner. And again, if you get a little confused,
it's a little complex. We went through that a little bit quickly.
Yeah, it's just, again, draw it out, and you'll be able to figure out, oh, this makes sense. Okay, I get it. Like, that's how you find the center.
The best way to do this is, draw it out, mess with the math a little bit, put some programs in, break it, try to see what's wrong, try to see what works, and then you'll get it right.
Yeah. So again, this sample code that we'll definitely give you the sample code. Yeah. So let's switch to the code.
Yeah. Okay. So let's dive back into the code of circle here. So we can start creating methods for this circle. And one of the most important ones that's actually going to put circles on the page is this create random circle. And it's going to help us create a random circle with a randomized size, randomized velocity, and a randomized color. So we have a few variables in here that help define the maximum and minimum widths and speeds. Some colors that Mark defined that he can change the different colors to. And then the width is going to be a random integer between those two values that we defined. The height's going to be the same as the width because it's a circle, so it's going to be circular. The velocity is also going to be randomized between the minimum and maximum that we created. The colors are going to be randomized. And then when we're done, it's going to return this circle with a velocity, a width, a color, a height, and then it's also going to put it, does this actually put this on the canvas, this application.canvas width, or is that just pulling out the width of the canvas that we create?
It's just going to canvas.
Okay, so it's gonna pass in the width and the height of the canvas as well. So this create random circle is a method which takes in the reference to the class and actually doesn't belong to any object. That means we can just call it straight out of the circle.
Like circle, like basically, yeah. I'll type this in.
Yeah, that'd be great.
I basically call this in the rest of our code.
Yeah, anyway.
Say great, we'll do this.
Yep. So like when you were working with Turtle earlier in the course, that was a really similar one, where you can do turtle.turtle and it will draw a turtle. This is the same thing. It's going to be create random or circle.create random circle, and it's going to throw a circle on the page. And it's not going to be any particular. It's not going to belong to any particular object, which makes it very powerful and useful. Okay. And then
like updated draw. Go through that. Yeah.
Yeah. Oh, so the final method that we have here is draw function, which helps us actually take in the canvas object and we'll draw a circle on that canvas object. So this goes back to the actual canvas that's been created. It takes that that white square and then helps us to draw a circle on it by pushing in the x value, the y value, putting in where it's going to be by using the width and the height, and then filling it using the color that we defined. Is there anything further that we want to talk about?
The update function too, because we're overriding. This is also overriding the update function.
Yeah, sorry.
Of the shape.
Oh yeah, so shape has its own update function, and it has. We're going to want something a little bit different for the circle class, and it's going to update in the same way. But then we're going to move the center
as well.
Yeah, we're going to move the center as well according to the x value and the radius, and the y value and the radius.
Yeah, because every time you update, the x and y changes. So your center needs to update along with the new x and y's.
Yeah, exactly.
So that's again just tells you how we would use method overriding. Good example case.
Yeah.
Right here.
Excellent.
And I think we have edge collision.
Edge collision. All right. So this is where the magic happens. We want to have the circle behave realistically by when it hits an edge to bounce off in a way that's believable. So the first way we've got to do this is create an imaginary box. We have the canvas, but we actually need to create a box that will bounce back the ball when it hits it. So we create a bounding box that covers the circle itself. So when that circle hits the bounding box of the square, then that's how we know the collision happened. Now we can make the bounce happen. So say for any edge on the canvas, if the edge is at or beyond the edge of the canvas, if the edge of the circle is at or beyond the edge of the canvas, we can say that the edge collides, and therefore we can change the velocity to have the object bounce back toward the inside of the canvas. So you have it up right now, the collision?
Right here.
Okay, cool. So the way we can check it is we pass in the object, we pass in the canvas width and the canvas height. So we check the top and the bottom edges, and if the object y is less than or equal to 0, that means it's hit the upper left corner of the canvas. And then if we want to check whether the bottom of the bounding blocks collides at the bottom edge of the canvas, we do the y value of the object plus the object height and check whether that's greater than or equal to the canvas height. And then we know that it's hit the bottom. So
what happens when we hit the edge? How do we set it to bounce back?
Right. Oh yeah. So when you hit the edge, you want to change the velocity of the function. And the way that bouncing works, we just want to change the y value. Let's say it's bouncing up. If we hit at the top, we want it to bounce down. So basically, we're just changing the y velocity from something that's positive to something that's negative.
Yeah, or just inverse it.
Inverse it, yeah. And then, well, exactly, yeah. So if it's bouncing down, it's going to be negative and then going back up. So it's going to be an inverse. So we want to change the velocity of the y to something that's negative of the velocity of y.
Yeah.
We're just going to flip that change. And we're going to do that also with the x. So if it's moving sideways, then we're going to change it when it hits the edge, and it'll bounce straight back. So this means that if we're moving even obliquely, it's going to help change it in the way that's exactly opposite the way that it came in.
Yeah, because the x and y are both changing. They're both inverse, so it will go back. If it goes here, hits, it will just go here.
Yep. And that's actually very straightforward. And
it's pretty straightforward. A lot of people get tripped up, I think, when they think about how do I do collision. It's
what if it's spinning?
You
don't have to worry about.
You don't have to worry about these things. Like where we don't, again, like how program works. Like you have this big problem. Just decompose it into like small little components, and then just deal with small things one at a time, like say just collision on the canvas. You don't need to worry about collisions in the with circles, or even if it's spinning. Like what's the angular velocity or angular momentum? I'm like, okay, well that's a whole different function to check to make sure. Okay, if it's spinning, okay, I need to my update function can't just be okay. Update my vectors. I need to update my function based on both vectors of this vector here, also this angular vector here. So like I need to like figure out how to do that, and
so
that's
I didn't
all.
take physics, Mark.
That's all physics, really. So this is actually a real world application of physics, and this is how you really model things.
Yeah.
That's really, this really, if you're interested in game programming,
yeah, it's huge.
This is huge, and this is where you need to start thinking about how to think abstractly in terms of 2D space and 3D space, and also understand the physics of objects when they collide, when they spin, all the things that you talked about when you're modeling a system in the physical world. We use that to model our systems in the computers. Just an FYI for our people who are interested in game development and actually programming gaming engines, and this is a good sneak peek.
Yeah,
I'll say.
You're going to be doing a lot of this.
Yeah.
A lot of arrays, a lot of vectors, a lot of
cosine tangents.
So.
Yeah, lots of vector decompositions, lots of linear algebra too, actually.
Yep.
So good stuff. So we're almost out of time. So let's bring it all together now.
Yeah.
So let's go back to screen sharing. So in this code, we have all these objects, and let's go back to actually really hit the basics of like how this application works. I create my widgets, I create my canvas object, and then I create my circles, and then I animate them, right? So let's go back to create canvas objects. So I'm going to create 10 random circles to bounce around. So basically, I just have a for loop, and then I tell them, okay, I have a list that it's an internal list that contains a reference to all my circle objects. So basically, I'm going to, for every iteration, I'm going to create a random circle, and then add it into my memory, and I'll be able to access it later on.
It's that easy. Huh?
It's that easy. Yeah. So basically, I could do this. I'm fine. That's it. So 10,000 objects. All right, that's great. I will probably crash my memory right now, but I'll just go back to 10. So let's do 50 right now.
You're crazy, Mark.
I'm crazy. So and then the animate thing, it's still update all. The update all function. Let's see. Update all. Yeah, the update all and the WeDraw functions are slightly different because now for every object that I have created in my update all, I will check that whether that object has collided. Okay. Change the velocity. I added a feature to check for circle collision. So if the balls collide with one another, then they should react and bounce away from one another. But that has not been implemented yet. So I'll show you what it looks like if you actually implement it in this code, and then you just call update, and like, okay, I'm just gonna after I calculate all of my collisions, I'm gonna update the position now, and based on the new vectors that I've calculated.
Cool.
Same thing as in WeDraw here. As you can see, for every object, I'm just gonna draw the object. That's
great. It's
a very simple way for me to even communicate with you what I'm doing.
Yeah.
So hopefully everyone could understand. Okay, in terms of let's see, object. Let's see. Sorry, that's okay. In terms of object,
are you still screen sharing?
No, I need to quit that messaging. Let's see. Let's go back. I need to re-screen share that. So let me show you. Tower screen.
Whoa,
recursion. Yeah, so basically, like it's just a way for me to draw and talk in terms of very intuitive ways. When I'm talking with another programmer or when I'm trying to think abstractly in terms of how am I moving these objects, I'm going to draw them, I'm going to check for collisions, I'm going to change them, and then you abstract all the details away, so the code is very readable, and very maintainable.
And if you want to do something else, you can do it right here, and that's not that much harder.
Yeah.
So if you want to do more objects or different objects, you can append different sorts of objects in once you create them.
Yeah.
So makes life easy.
Makes life easy. So this is 50. These are 50 random objects random circles that I created. So yeah, still works pretty well.
Cool stuff.
Cool stuff. And let's see. Let me pull up the code for. Where's the code?
What's the bonus round?
The bonus round. Final. So basically, this one will have. Oops. Let's see. No. Oh, line 76. There's a typo. Sorry. Okay. Bonus round. Here you go. There you go. So once you've updated your the function to do object to object collision, this is what it will look like. And this is the secret, the key of actually trick. And once you're doing this, if you can't imagine procedural program, you have to literally check every single object and literally calculate the collisions and the vectors for every single object at every single time at every given point in time.
There's no point in having computers if you had to do that.
Yeah, so you get the computer to actually handle that for you. So with object-oriented programming, you just basically program the object itself will say, I have a function, I'm going to look out for myself. If I collide with anyone else, I'm going to change my vectors and my path based on my own collision, my own way. So you don't need to think about it from a top-down approach. You think about it from an object bottom-up, bottom-based approach. And these objects, these objects are self-contained and they kind of act on their own.
Mm-hmm.
It's kind of like you're programming an army of things that could think and act on their own, with you not having to track every single thing.
Yeah, you just give them guidelines.
Just give them guidelines, and then they'll just go ahead and do it by themselves. So that is hopefully this gives you a really good application to play around and also to think about object-oriented programming. So do you have any last-minute thoughts, Jonah, on object-oriented programming in general or what we did?
I thought it was a really cool start. I thought that analogy to the video game programming is really good. I mean, object-oriented programming is going to be important in anything that you do.
Any big project.
Yeah, any big project. Even in life, I think.
In life, whoa.
Yeah, think a little bit bigger here. It's good to isolate certain tasks. Like let's say like in the mornings, I'll go through and do all the reviews, but I have that isolated as its own task, and then I'll think to myself oh, this reviewer needs to have an email. It's already a predefined set of tasks, and I don't have to think through it every single time.
Yeah.
There's little things that I change each time, but yeah, if you think about abstraction in a greater sense, it's useful to apply to a lot of different things. And it's kind of cool to see how you can apply it here.
Right. Yeah. So my final thoughts is object-oriented programming is a little weird at first, but it's I'll say at the end, if you're thinking big, you're basically programming the computer to take care of all the little details for you and make a system that each object will be able to take care of itself, and it knows what it needs to do on its own, and it knows how to update its own state.
Yeah.
You don't need to literally go through all your objects every time a state change. There's one change of state for one object. You just program it that in a way that the object itself will take care of itself.
That's what makes computers powerful.
Yeah, right? That's a really powerful way of thinking, and once you get it, it will stick. It won't go away. So, okay, great.
All right.
Thank everyone for
coming.
staying, and we'll post our notes in this example code so you'll be able to play around with it yourself.
All right. See you guys next time.
Bye.